Hi everyone, today I'm doing this abacus tutorial and I'm going to show you how to simulate a tensile test on a steel dog bone specimen using a 2D model with plane strain thickness. This is easier than trying to model this in 3D, and it's great for quick stress strain evaluations. So yeah, I guess we will start. So first, I did the modeling already, so we can take a quick look at the part. And we want to kind of just examine how I created this. So we'll see the dimensions here. You can see this top part is 25 by about 20. The radius of this is 25. The length of from this section to here is 50. The total distance from the top to the middle, the midpoint, is 90, and we're working in millimeters. And right here you can kind of see the width of this is like the total is 10, so you want to do half. And I did this by creating this top quarter, and then using the mirror, I created the second half of it, and then just mirrored over this midline to create the bottom half. So that's a quick run of what I did to create the part and the dimensions. And let me just regenerate this really quick so that we can move on. And the next part is the property, which is just based on steel properties. So we can take a quick look at this. I named the property steel, and the first thing I did was create the density, which is 7.8, 7.8 e to the negative 9. And then from there I created the elastic, which is just right here, the elastic property. And we use a Young's modulus of 210 e to the 3 and a Poisson's ratio of 0.3. And I put in this field of plastic stress and strain. Let's expand this a little so we can see the full thing. So there's 8 total values. You can kind of look it over and insert that little plot or little table. The next thing is, we did this. You want to do a damage for ductile materials or metals, and you want to select ductile damage, which is right here. And this kind of just gives the model something to work with for ductile damage. And we also want to put damage evolution, which you can see right here. Maybe. Yeah, so we want the displacement at failure to be 0.2 millimeters, and we leave the rest of this alone. So that's a little rundown of the material properties. And then we want to create a section which is just steel homogeneous, and I did a plane strain thickness of 0.05, 0.5. And yeah, that just kind of tells the program how thick the specimen is. And I just assign the properties to the part. Next, I did assembly. You just add the dog bone, which is all of the given stuff here. And in assembly, one important thing is to create this reference point. And to do that, you want to use this tool, which it creates an offset, and you just click this middle node and then offset the reference point 10 millimeters in the y direction, so just positive 10, and you leave the x and z 0. And yeah, so that creates an offset, and then from there you need to go to tools and assign that point as a reference point. So I've already done this, and I'm just kind of going over the steps. And from there, well, we're done in the assembly module, and we want to create a step. And this is pretty self-explanatory. We can go into the properties. One thing I did is select dynamic explicit and change the mass scaling. We want to put in this time of 1e to the minus 4, and that's one important step here. But the step has already been created, so we'll dismiss that. And then the next thing we want to do is create an interaction between the reference point and the surface. So to do that, I clicked Constraint Manager. We can look at the coupling. So it's coupled and it's kinematic, all degrees of freedom. Click OK. And now the load, we're not actually applying a load. It's going to be 2 boundary conditions, which here is the bottom, which we can see is just encastered. So you just select the whole bottom and caster it. And then the second one is going to be this displacement at the top. So for the initial step, you choose initial, and then you're going to select U1 and UR3. So we don't want it moving in the X direction, and we don't want it to have a moment. So that's good. And then the important part of this is the modified. So on the dynamic step, this is the second step, we're going to edit that and put a displacement of 10 millimeters in the U2 direction, which is the Y direction. And we're going to create, this is kind of how I did it, just create an amplitude, tabular, and then the time and frequency is going to be 0, 0 for the amplitude, and then this one is going to be 10 and 1. And so this kind of just tells you from 0 to 10 seconds, we want it to go from 0 to 1 displacement. So it's going to displace the full 10 millimeters in that 10 seconds. Okay, so that's how I did this part. I've already done it, and then you want to make sure it's not instantaneous. You select the amp that you did, or the amplitude that you did. So that's all been done already. And the next step, we're going to mesh the part. And to just kind of show you, I did 2 different meshes, one for this top part and the bottom part. So you can select this, hold shift, select this. And the element size is 5, and we left everything else alone. And this middle part we did 1.5 for the element size, just to get a finer mesh in there to see the details of what's going on. So everything else is good, we just leave everything else alone. And then we want the element type to be standard linear reduced integration. So it's going to be a CPSR4 or S4R. So that's, and then this one, it's going to be the plane stress. So we'll leave that as is, cancel, and then you want to go ahead and mesh your part. So it's already been meshed, but next is we create a job, and which I've already done. You just want to create job, use the whole model, and everything, we just want to leave everything the same. And so now we can submit. And we want to see the results. So this kind of just shows you the results. This is the end result. It shows you the stresses, it shows you the displacement, and we can just kind of look at this little simulation. Okay, and to see the results, we can click this, and it'll show us a little animation of the tensile specimen. We can zoom in and kind of watch where it pulls apart. You can see necking, which is pretty cool. Let's go look at the stresses. So you can see it's under stress, and then as soon as it breaks apart, there's no more stresses, which is pretty cool. So let's zoom out. Yeah, it's pretty cool how you can see the necking right in that region. So the next step that we kind of want to examine is we want to look at the stress strain curve. So we'll do XY data, the ODB history output, and we want to see the reaction force and the spatial displacement. So we can just hold shift, select both, and plot. And this kind of just plotted both in two separate things. So instead of doing this, so we can just use a plugin, go to Tools, and we can export this data. So we can do from Abacus to Excel the XY data, and then we'll just choose what we have, the displacement and the force. So we want to choose that and that. Okay, and it is popping up a little Excel sheet here. It's right here. So it kind of gives us two sets of data. This first column and this third column are going to be the time. So let's go label these so we know what we're dealing with. This is going to be the force, reaction force. This is also time, and this is going to be displacement. So in order to get a true stress and strain curve, we want to do the force, so this column, divided by the cross-sectional area. So let's do that. And then we also want the original length so that we can get the strain. So we will divide this displacement column by the original length. We'll do that. Length. And so the cross-sectional area for this is going to be 10 because it's just 10 millimeters by 1 millimeter. And the original length is 180 millimeters. And so we're going to create two new columns, stress, and this will be the strain column. So stress is going to be the force, we'll do equals force divided by the cross-sectional area. We'll just drag it down. That'll be easiest. Okay. And then the strain will be equal to the displacement divided by the original length. Okay. And then we want to plot these two so that we can see what it looks like. Okay, we'll select the data. So we want the Y range. So we want the Y data to be the stress. And we want this. Okay. And we'll edit the strain. So it'll be this column. And that should show us our plot. Yeah, so we can see our stress strain curve here. You can see it kind of ramps up. So if we divide, or if we get the slope of probably either of these, we can probably get the Young's modulus. So after it kind of looks like a typical stress strain curve that you would see. This kind of, these points are a little irrelevant. We don't really need that information, but you can see where it kind of breaks. Like this is the necking, and then it finally, this is where it breaks. Yeah, so that is my tutorial showing you how this works. Yep, that's it. Thank you for watching.